Hi, how's everybody doing today? Today, we will investigate the fourth experiment in Labflow, which is kinetics of an iodide reaction and is called kinetics of an iodine clock reaction. Kinetics, as you know by now, is the study of the rate of chemical reactions. And the rate is the measurement on how fast the reaction takes place. That's why it says clock reaction. In our case, we are going to use a stopwatch to measure the speed of the reaction. The objective of the experiment today is to find out the rate law of the reaction between iodide and bromide in acidic conditions, and also to calculate the rate constant. So as we always do each week, I will give you a quick overview of the experiment first. Then we will do a learning check to make sure, answering questions to make sure the main concepts are there and you are ready to go to the pre-lab quiz. And towards the end of the workshop, what we always do is go over the report and go over the calculations that you will need to do in order to complete this week's report. So let us start by sharing the page of the experiment. Please, if you have questions, don't hesitate to stop me. This is a workshop. It's supposed to be interactive. So stop me or raise your hand or unmute your mic and let me know. This is important that you follow me all the way. So let's look. When you click on the left of the experiment, this is the first thing you are supposed to do. Just read the experiment. So we will go over this. So here what we see a chemical reaction here. So we will study the kinetics of the reaction between iodine and bromide in acidic conditions. And this is the reaction here that we will study. And we will measure the rate of this chemical reaction as the change in concentration of the reactants or products. In our case, we will see how we are going to measure the rate. We will use an indirect method, measuring how the concentration of iodine changes over time. So the rate, the first thing that we know, here it says rate. What is this? The first part of this equation. It says, this is an example, it says delta, which is the change in the concentration of bromide. In this case, they picked bromide over time. This is how we define the rate. If we are trying to see the rate or the speed of a car, we are going to say how many miles in a specific time. Here is how much the concentration, either a product or either a reactant, changes over that specific time. So if we have a chemical reaction that has a slow rate, means only a small fraction of the molecules will react to form products. Let's say in 5 minutes, we measure, let's say delta T is 5 minutes. So if we have a small rate here, means the numerator is going to be small. The delta, the change in the concentration is going to be small, only a small fraction. But if we have a high rate, we have a fast rate, large fraction of molecules react. So we are looking just as the first part of the equation. And how are we going to measure the rate? We are going to measure the rate by measuring the time that will be given to us. In our case, we will go over shortly the time from 0 until the time that the first blue, which is the color of the iodine with starch, appears. So one person is going to be, if you are in the lab, 2 people are going to work in groups, in a group of 2. So while one is adding the last region, the other starts the stopwatch. And then you measure the time. So delta T will be the time. And we'll see how we are going. We are not going to measure in this experiment the change of bromate. We will go over that. But I just wanted to point out that how do we measure the rate? We measure by change of concentration over time. Any questions there? I'm sure this is basic and you've seen that in lecture. I just wanted to connect with the experiment today. But what is interesting about kinetics is that as long as the reverse reaction is very small, the reverse reaction is the one that goes the other way, as long as that reaction is very slow, we assume that in this experiment, we can express a relationship that is called rate law, which is what we are going to calculate today, between the rate of the reaction, which is this, and the concentration of the reactants. And this is what is called rate law. The rate is going to be the product of the constant times the concentration of all the products. Let me erase here. So this is the rate law, the whole thing. This is the rate law. This is the objective of our experiment. We will measure the time. We'll see how we're going to measure the rate. And then we will calculate the constant, and we will calculate all these exponents. It's going to take some time. A, B, and C. This is all what we have to do today in this experiment using the rate law. This is what is interesting, that not only we can measure the rate by changing concentration per time, but also we can express this relationship about the constant times the concentration of iodide raised to a number times concentration of bromate raised to another number, and the concentration of protons raised to another number. Now, it's very, very, very important that you know that these numbers are called order of the reactions, are only determined experimentally. Never think that it has something to do with the coefficient of the reaction. No, 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 has nothing to do. We have here the balanced equation, right? Very good. But experimentally, the objective of today's experiment is to obtain A, B, C, and the constant. How are we going to do that? Let's see what else. It says here that we are going to use the method of initial rates. This is how we are going to calculate the order of the reaction and the constant. What is the method of the initial rates? Basically, to find the value of the rate exponents, which is A, B, or C, we vary the initial concentration of one substance. Let's look at the reaction here. The reaction has three reactants: iodine, bromate, and protons. So what we do is we do different runs, different reactions, and we keep the concentration of one, let's say iodine, let's say we vary one and we keep the concentration of the other two constant. Let's move and we are going to see examples. For example, here they are showing. We are going to run a reaction with we are going to measure one rate here and see when they write here, they say, okay, this is the rate law for this specific run. The constant is the constant for that reaction. And then iodide has concentration 1, but bromate and proton has the same concentration as in rate 2. Does it make sense so far what they are doing? We are writing the rate law. Rate equals K times concentration of one reactant. We have here the 3 reactant raised to A times concentration of bromate to B, a concentration of protons to C. But the method of initial rate is vary one of the 3 and keep the other 2 constants. Why? It's just a mathematical thing, not much other reason. So when we divide the second equation by the first equation, right here, what happens? They divide this by this, right? But actually they do. Rate 2 divided by rate 1 here. So because constant is the same, it's going to cancel. And we basically did that on purpose. We use the same concentration of the other 2, and the only one that is different is the iodine. So we are trying to calculate with this in this way the exponent A. So we will have the rate 2, we will have the rate 1, we will have the concentration of iodine 2, iodine 1, and we are going to calculate, we are going over the calculations later, we are going to calculate A. And then what do? We need B and we need C. If we want to calculate B, what do we need to do here? Let's erase everything. If we need to calculate B, which one is the one that is going to vary? And which one is the one that is going to be constant? Somebody can text me. Which concentration do I need to change? And which concentrations do I need to keep constant? Somebody can tell me. If I want to calculate B, the one that I have to change is bromate. And all the others have to be the same, because when I divide one with the other, then the only one that survives is the one that is different. But we'll go over that. This is just a quick overview. Any questions so far? Okay, so let's go over. How are we going to measure the initial rates? We use an indirect method. We use the reaction let me see here. So if we look at this reaction here, just to understand the whole picture, we are trying to find out the kinetics of this reaction, right? Okay. How are we going to calculate the rate? We are going to calculate the rate of iodine that has a nice color. How are we going to calculate the rate of the iodine in this reaction? We are going to use an indirect method. As soon as it's produced, the iodine, here, we are adding also to the reaction thiosulfate. And then the thiosulfate is going to react with the iodine. And this is with, we are going to have starch, so the iodine with starch is blue. But because thiosulfate is going to be in the reaction, is going to disappear the color. As soon as all the concentration of thiosulfate is used, the color is going to show up. We will go over more and we'll see how to go step by step. But basically, this is the first introduction. We are going to calculate the rate of the iodine using an indirect method. And how are we going to use it? We know actually that the iodine forms a dark blue complex with starch. Actually, because there is also iodine, instead, they both behave the same, right? So don't get confused with that. Here they want to talk about the triiodine, but consider that is iodine. So we don't add one more point of confusion. And as long as we are going to add a specific amount of thiosulfate in that reaction, it's going to be already in this here. So we are going to have the iodine, the bromate, the acid, and the thiosulfate, which means that as long as the thiosulfate ion is present, the iodine, or triiodine as they want to say it, produce the first reaction is consumed by a thiosulfate ion. The moment all the thiosulfate is used up, or the concentration is zero, the ion forms a dark blue color of the starch complex. So we are going to add everything. One student will add the last region, let's say bromate, and the other student will put the clock, 0. And then as soon as you see the blue, you stop clock or stopwatch, and you are going to measure the time that the blue appears, and then we will see how the concentration, we are going to look at the change in concentration of the thiosulfate. So if we look at this, because we need to know how to calculate the rate in order to get the rate law. Because when we divide, and if we are going to use this to calculate A, we need to have the rate 2, rate 1. So we are using an indirect method. Let's look at this here. So this is the explanation. So basically, the rate of the reaction is going to be calculated with this equation. Why is that? It's going to be the change in, that's why they say it's an indirect method. Why? Because the delta means the change in concentration of the iodine, right, over the time that the students measure. And because, let's look at this reaction right here, this one. You know that this one has a 1 as a coefficient. The thiosulfate here has a 2. And because it's on the reactant side. As the reaction moves forward, the concentration is lower. That's why we add a minus here. Minus, then we add the 2 because of the coefficient. The change in concentration of thiosulfate over time. But because when we see the blue, the concentration of thiosulfate is 0, we end up with this easy equation. This is how we are going to measure. So if you don't remember the whole thing, just know how to calculate the initial rate. How? Using this equation. Half of the initial concentration of thiosulfate divided by the time that is going to be given. Okay, so this is how we are going to calculate the rate. And then we will go over the report, but I just want you to start looking at the whole experiment. And here, they are talking about experimental. So if you look at this, I just want you to look. These are all the regions that you have in the reaction, right? And they tell you how much you are going to add here. So basically, let's look at this. Here it says experiment, right? So a 1, 2, 3, 4, 5, 6, 7. Each group will run 7 different experiments because we need different concentrations. And then we have potassium iodine. We have water to make the volume the same. And then we have acid. We have starch to see the color blue because of the complex that forms with the iodine. And we have here the thiosulfate. So the experiment goes that you add 300 microliters of this. Let's look at A1. 600 microliters of water, 300. You will need to use this table for the first calculations. And then how the experiment goes if you are really in the lab doing this. It says here, final region. That means that nothing happens until you add the bromate. So the final region is the bromate. So you prepare boom, 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 everything but the final region. Then you add the final region, and at the same time, you start the stopwatch. And you measure the time until you see blue. So this is different experiments that is showing you here. And then the calculations that we will go over when we see the report. I think it will be much productive to do that while we are doing the report. I think it will make sense. Otherwise, you probably will get lost. We'll go step by step by looking at the report. Any questions so far? Was it clear so far? Okay, so then we'll go over some learning checks before we will go over the report. Let's share the page of the learning check. Okay, problems like this are, okay, let me see. Will we have the same, I have a question here. Let me read it. It says, Kevin, will we have the same reaction for the lab report as one in the experiment? Yes. Everybody will have the same reaction that I have, which is an iodine clock reaction. But everyone, that's why I'm going over in detail, but everyone will have different data. So I will show you how I did it, but you will have to do the calculation, and it's a lot of calculations, because in order to calculate the first exponent, let's say A for the iodide, they do 3 experiments. So you get 3 values of A's, and then you have to get the average. Then for B, same thing. So everyone will have different numbers, but it's the same reaction. Everybody's studying the reaction between iodide and bromate in acidic conditions. And everything that I'm explaining now on how to calculate the initial rate, everything applies to your experiment when it's time for you to do the report. Yes. Did I answer your question? Okay, so let's look at this first experiment. First problem. Why I add this to the learning check? Because there are some problems in the pre-lab quiz that are similar to this one. I usually put stuff you will need to do. If this is very easy, we can skip and go to the next one, because this, I think, once you finish Chem 1, you are able to do this. So let's read it and see if it's easy. A lot of things like that will be in your pre-lab quiz. So here it says, glucose, they give us the molar mass, is a simple sugar. Glucose are used to treat patients with low blood sugar. Suppose you prepare a glucose solution using the described procedure. And they said, step 1, dissolve 290.8 grams of glucose in enough water to make 500 ml of solution. So first they do that. And second step, they transfer 16.3 ml of the solution to a new flask and make a dilution to 250. And they ask you for the concentration. And now I'm asking you, would you like me to solve this problem, or would you like me to skip it? Okay, so let's do it. You will see some similar in your pre-lab quiz. And so let's look at this. This is just a very simple problem. It's a problem of dilution. But just to refresh, the first step, what happens? They dissolve 290.8 grams of glucose. And then what do we need to do? What would you do first in step 1? First of all, we need to calculate the concentration in step 1. How do we do that? We want to know the molarity in step 1, right? They are giving us the grams, right? So concentration, yes. Somebody says convert to kilograms. Yes, not convert to kilograms, because molarity is moles per liters. Yes, exactly. Here I can see moles divided by liters. Yes, Michael. Yes, okay. Yes, that's molarity. Yes, exactly, Alonso, correct. A molality will be, in this case, we are not talking about molality. We already passed the freezing point, the colligative properties that we use molality. But the big M is molarity with an R as in rose. So basically, molarity is moles per liter. So Michael, you were right. Yes, exactly. Very good. Okay, so 290.8 8 grams because we need moles per liter. Let's refresh. How do we change? They are nice. They don't make us calculate. They give us the molar mass, right? So the molar mass says that 1 mole equals or weighs 1 mole of glucose 180.16 grams. That's what we use the molar mass for, right? So we convert it into moles, but we need to divide by the volume, right? Molality, this big M1 in the step 1 equals moles that we have already divided by the volume in liters. So these people say 500 ml. We have to convert it into liters, which is 0.45, let's say 0.0 liters. If we do that, we get the molarity in step 1. And then, once we have that, that is what number do you get? Okay, if not, then we have to calculate M2, right? Because then once we have, okay, somebody told me, M1 is 3. Alonso, thank you, 3.23, perfect, moles per liter. Awesome, thank you. Now, once we have the molarity of the step 1, what do they do in step 2? They say transfer 16.3 ml of solution to a new flask and add enough water to make 250 ml. That's a dilution, right? That's clearly a dilution. We get some volume and dilute it. So what is the equation for a dilution? V1 M1 equals V2 M2, right? But we are looking for M2. So if we divide both by V2, we are going to have M2 is going to be volume 1, molarity 1, divided by volume 2. So what is the volume 1? Transfer. Look again, Michael. Volume 1 is the volume that we take from the solution that has the molarity 1. Yes, yes, thank you. So in this case, because usually we have to convert into liters, but because we have the 2 volumes here, one up and one down, we can keep it as a milliliters because they're going to cancel out. So the V1 is the volume of the solution that has the molarity 1. So times, what is the molarity? 3.23 divided by, what is the volume 2? Is the volume of the solution that will have molarity 2. And that is 250. Yes, we can do, if I put 0.250, that is correct, I have to put both volumes in, either I put both volumes in liters, exactly. In our case, I didn't want to take the work to convert, so I left both in mLs because they are giving me. And I obtain an M2. Okay, very good. M2 I have a value of 0.21 molar. Okay, this is what I obtained. Okay, awesome. Any questions there? It's just a little refresher, but you will see it in the pre-lab quiz. So I wanted to go over that. Let's go to the next one. And this is also something you will need to do, more related with kinetics. So let's read the problem, because this is similar as you've been doing that in lecture. So you are familiar with this. I believe it's not the first time it's presented to you, but it's important that here you are a pro in this. So let's read it. Suppose you are studying the kinetics of the reaction between peroxide disulfate, which is this one, and iodide ion, which is this one. You perform the reaction multiple times. That is important. If they ask you how many times you have to use this method, how many times you have to run the reaction for this method, several times, many times. So in this case, you perform the reaction multiple times with different starting concentrations and measure the initial rate for each, resulting in this table. So here we have 3 different experiments, 1, 2, 3, and we are studying this reaction, and they already measured the initial rate of these 3 experiments. We don't have to use a clock. They give us the 3, and they give us different concentrations. And they say, based on the data, choose the correct exponent to complete the rate law. So what would you do when you have that in a, let's say in a pre-lab quiz or in a quiz or in an exam? What do? You basically examine the impact of each reactant. You have 2 reactants here, by comparing 2 experiments. You have to pick 2. You have 1, 2, 3, but you have to pick only 2 because you are going to divide one over the other. So you have to pick 2, where one experiment, when one concentration is the same and the other changes. Does it make sense? So let's say I want to calculate the exponent of peroxide disulfate, this one. This is important because you're going to see this in kinetic a lot. So I'm trying to get the exponent of this one, right? And I have the rate law here. The rate law is written here. Is K times concentration of one reactant, which is peroxide disulfate, raised to A times concentration of iodide raised to B. And the problem asked me, okay, calculate A and B, which is similar to what we have to do in the lab. So if I'm looking for this, for A, what do I need to do? If I'm looking for A belongs to the peroxide disulfate. So I need to find 2 experiments in which the concentration of peroxide disulfate is different. Let's say here is different, but the concentration of the other reactant is the same, because if it's not the same, it's not going to cancel. Does it make sense? Okay, so then if I divide rate 2 rate 2 divided by rate 1, what do I get? The case cancels, right? So then all I will have is 0.4 divided by 0.27, all raised to the A. And this is going to be, what is the rate to 3.06 divided by 2.05. Does it make sense? So what is the value of A that you obtain? You can do it. If it's easy, you can do it in your head. If not, you will have to say A times natural log of this number equals this natural log of the other number. But this should be easy. So what is the value of A that you obtained? Somebody can text me. Yes, awesome. Thank you. Very good. Awesome. Now tell me what is the value of B? But what are you going to, in order to calculate B, what are you dividing? What two experiments are you going to pick? Yes, awesome. Thank you. Awesome. Experiments 2 and 3. Awesome. Very good. Why is that? Because the concentration of this is the same and this one varies. So what value you have for B? Yes. Yes. Even if you do the other way, it's okay. I usually put in the numerator up the bigger number of the rate because it's easy mathematically, but it doesn't matter. You can do 2 divided by 3 or 3 divided by 2. It doesn't, rate 3, yeah, you can do either way. You're going to have the same number. Okay, I obtained B equal 1. Awesome. 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 Okay, so this is what we will be doing in the report, part of it. So it's important that we understand. Awesome. Okay, so then we can move to the next one. Not this one. Okay, so problem 3. How is the initial rate calculated in this experiment? We went over a little bit. I went over that we use basically an indirect method, but I don't really want to confuse you. So the way we are going to calculate the initial rate in all our experiment is going to be a half. This is the calculation you will have to do, times the initial concentration of the thiosulfate, the initial that will go over that, divided by the delta T that they will give us that data because you're not in the lab doing it. So this little 0 is the initial concentration of thiosulfate divided by the time provided and multiplied by half. And that comes from the equation that I showed you before. But this is how we are going to calculate the initial rate in this experiment. And then the last one, how is the reaction performed in the method of initial rates for a kinetic study. We saw that, right? We just did it, actually. The concentration of one reactant varies, while the concentration of all the other reactants is held constant. This is called the method of initial rates. And there is another question. How many times is this reaction performed? Several times. That is the answer, several times. Okay, any questions so far before we go to look at the report? Okay, this is what you are going to see in when you get to the point that you do the report. I have to warn you that this report, you will spend a lot of time doing calculations. Many, it's not difficult because we just went over the concept of what to do, and now we're going to go step by step. But you will have to do a lot of calculations. If you feel comfortable using an Excel to do the calculation, please do so. If not, you can also use your calculator and do the calculations. It's whatever is easier for you. Here I have a question. Is this data for this table given for the lab report? Yes. This is whatever you will see, Kevin, in red is given. So you will find this given in red. Whatever I have in green is something I have to calculate. So we will go over. I will show you my Excel sheet because I did it a lot of calculation in Excel, but you can use whatever you want. It's just time consuming. So don't wait until the last minute. Some others are much faster, but this one is time consuming. So let's see. When you open the report, let's say, okay, are you doing it online? Yes, blah, blah, blah. And then you open the first part and you will see this. All this is given. What is this? So you are familiar. Here it says reaction times in seconds and identification of comparison pairs. So basically, 4 groups perform: group 1, group 2, group 3, and group 4. Each group perform A1, A2, A3, up to A7. So each group performed 7 experiments. And what is this? A1. A1 is the stopwatch. Is the time that you are going to need, is the time between you drop the last reagent, which is the bromate, and then you start the stopwatch until you see the first blue, the color blue. This is the time, 95 seconds. So each group did 7 experiments. That's why it's a lot, it's time consuming, because you will have to average all these groups. So this is just at the beginning. They are giving you 4 groups and 7 different experiments. You don't have to do, for now, much. What is in here is given as well, because it's in red. You will have that too. This is actually a very good help. When I had to do it, I didn't get this help. So this page, use it because it's very helpful. Here it says numerator. It says, basically it's like that. Let's read to the left. first comparison pair for exponent A. So that means the first 3, see when we have to pick 2 reactions in order to get the order of a specific reactant. Okay, so basically when these 3, we are calculating A. A is the order, if you look at the experiment, is the order of iodine. You will see. So basically, they are helping you because they are telling you, okay, the numerator, they give you 3 experiments, and then you will have to average. And they say, divide A2 by A1, and you are going to get A. We will go over that, but this is a help. Then they have 3 different experiments, and they tell you, okay, divide, numerator, divide A4 divided by A1, and you are going to have, if you do rate divided by rate 1, then you can calculate B. And then they do the same for C. So this is a big help that is given here. You don't have to look, oh, which one, you need to pick 2, right? And they already are telling you, okay, these 2 for B. Does it make sense? And you should actually make sure that this is true. I did it because I wasn't happy. I'm like, okay, is this true? But yes, you will notice that when you divide A4 divided by A1, you can calculate the coefficient B. This is all given. Somebody said, Kevin says, I need to see the calculation in order for me to understand. Of course, I want to go over that. For now, I'm showing, of course. And then 3, because this is in green, these are calculations that you will need to perform. So this is the first, and see how many. This is a lot. So what is the first table that you need to calculate? Basically, what they are saying is record concentration to 3 significant figures. They are asking, what is the initial concentration of thiosulfate in A1, A2, A3, A4? What is the initial concentration of iodide, bromate, and acid? So basically, you won't do for the starch, you won't do for the water, you do it for the sulfate, the iodine. You have 4 different reactants. This one, remember, is to calculate the rate. And the other 3, you are going to use them in order to calculate ABC. But now I want to show you how I calculated these values because they are in green and you will have to do it. So we have many options. Let me start sharing. First, I quickly will show you the page of which data I used in order to calculate this. And then I'll show you my Excel. So let's start by sharing. Yes, thank you so much, Michael. Correct. I don't know if you can look at that while I'm teaching and showing something else. You probably have it printed, and that will help me a lot. Okay, exactly, Michael. So this is basically the table. So the first that you will have to do is they are providing you experimental, right? What are they saying? That you are adding for experiment 1, you need to use this table. You are adding. Let's do experiment 1 first, and then you'll know how to do all the rest. The first part, you are adding 300 microliters of iodine, 600 microliters of water, 300 microliters of acid, 150 microliters of starch, 150 microliters of thiosulfate, and 300 microliters of bromate. So when they ask you, what is the initial concentration of iodine, basically you are making a dilution. You are making a dilution because you added 300 microliters of this concentration, but then you add a lot of water after, a lot of ingredients later, or reagent. So let's say we want to calculate the initial concentration in A1 of potassium iodine. How do I do that? You know, in a dilution, initial volume times initial concentration equals final volume divided by final concentration, right? So how are we are going to use this equation for all the calculation. Let's say I want to use I want to calculate the initial concentration of iodine. So let's say I have the initial concentration of iodine. It's going to be the volume that I add, the initial volume, that is 300 microliters, times the concentration of the iodine that is given, is right here, 0.0100 molar, and divided by what? The final volume. What is the final volume? Is when you add the whole thing, 300 plus 600 plus 300 plus 150, the total volume is 1800 microliters. And that's how you calculate the initial concentration of iodine in A1. And here at the end, if you have some questions, they will show you. See here. Here they give you a quick help, some help. So they say, if you are stuck, table B, they help you with that. Calculate the initial concentrations of each substance and starch, except for the water and starch, for each experiment using the following formula. And then what do they do? If they are using, we did the iodide, we did the volume times the concentration of the solution divided by the final volume. And then they give you, for example, they did what I did. They say, for example, the initial concentration for experiment A1 are, and they show you. This one is what I did for A1. It says that I have a chat. Okay, no, I thought somebody wrote something. Okay, so is this clear? Does it make sense how you are going to calculate? Let's look at bromate. Let's go back to they say that they use 300 microliters and the concentration is 0.04. Let's look if that's true. Let's go to the table and we look in A1 and we look in bromate that is here, and yes, they use 300, the concentration is 0.04 divided by the total volume. So this is the first table. And now I would like to share my screen on how I did it. If you want to save time and use Excel, but it's up to you. I mean, it doesn't matter. But let me share mine. So this is how I did it, because I wanted to save time, because time is always an issue for me, for everybody actually. I mean, this is time. So look at my thing. It's a lot of numbers, but let me tell you something. So here I wrote the tables. I wrote the A1, A2, A3 here. And then I wrote the volumes. Here I have the table that I just shown you. This is the table. And then I use these values. And then next to it, I wrote the other table, which is the times. It will be up to you. It's a lot of numbers. But for me, it was helpful because I calculated, okay, the concentration of the initial concentrations, I had it all there. And then how I calculated just with a formula. So this is all the initial concentrations. And this is all the range, we'll go over later, but basically the yellow here is to calculate A is iodide, and I obtain A equals 1. How about with bromate? I did everything and I obtained a B, also 1. So B is for bromate, and then for the proton, this is I obtain these three numbers for C, and then you have to calculate the average. But let's go over, because this is, if you are familiar with Excel and you want to do it, but if it's gonna take more time, just do the calculation quickly, boom, boom, boom in the calculator, and it should be good. So let's go back to the report and share what else comes later. So we know how to calculate the initial concentration. That is one thing that we have to do. Okay, so this one we saw is given. This one is the help of what do we need to divide. And this one is what we just seen. Any questions on how to calculate the initial concentrations? Notice that maybe if it's an exponential, you will have to write it like I did here. See, 8.33, and then you write a big, like in Excel, big E. Is time involved in the calculation? Yes, time is, Alonso, time is involved. That's why this takes forever. So we are gonna get there. This is the first step. We have the basically the initial concentrations. Now, for this table, would time be in the calculations or not? No, Kevin. For this table, no time. We only use, I show you. Yes, exactly. Let me see if I missed a question. For this table, no. Okay, so this table, you already know how to do it. And I show you that at the end of the report, if you forget or you don't want to watch this again, you have that quick help that is showing you no time involved. It's just concentration because it's a dilution. And then what else comes next? Let's look what else. Okay, here the time comes. Kevin was asking, Kevin got it. Okay, so this is a table that we bring back the values. Some were given, and whatever is in green, I had to calculate it. So the average reaction time here is very easy because obviously 95.6. That's why I use Excel. It's going to give you the average in video. Otherwise, you do 95.6 plus 105.4 plus 97.7 plus 101.4. This is the times that are given at the beginning, divided by 4, and you obtain the average. So this is the first column, and this is the easiest column. So this is when we are using the time. And then comes the initial rate. How are we calculating the initial rates? We talk a little bit about it. Who remembers how we calculated the initial rates? Okay. We mentioned when I explained that we use an indirect method, and it comes basically let's see if there is space here to write. Okay, so basically the initial concentration, any of these, is going to be the initial rate half of the initial concentration of thiosulfate. In my case, I'll show you later, but let's do this. Divided by the time. Which time? This one, the average. So, for this value, which one is the initial concentration of this? Let's look at mine. Where do you see my initial concentration for A1 of thiosulfate? Remember, we are going to use the initial concentration of thiosulfate to calculate the initial rate. For the order of the reactions, we are going to use those three, or those three, A, B, C. But this one, the initial concentration of thiosulfate, we only use it to calculate the initial rate. So for me, it's this value. And you will have it in your table because you will have to do that. So if you look down, it's always the same for the 7, right? So then let's go back to ours, and it's a raise, but that's okay. How are we going to calculate the initial rate? We are going to say it's a half of what I got. You will have it in the previous table. That's why it's so time consuming. I think the next one is not that bad. Okay, so this is the concentration of the thiosulfate divided by the time. Which time? Let's say I'm calculating for A1, right? So it's going to be 100 0.03. It's going to be the average of the 4 groups for A1. And this is the initial rate for A1. Any questions so far?
I have a question.
Yes.
Do we only use S2O3, or do we use any of the other ones? Like, do we use the iodide or the hydrogen?
Okay, this is we are going to use everything because I didn't finish. I just want to make sure that, yeah, so the thiosulfate, we only use it to calculate the initial rate. We are trying to calculate, remember, we will need to divide one. We will use the method of initial methods. So we will use basically the rate 2 divided by the rate 1, and then we need to have this initial rate. And in order to calculate the initial rate, we use the thiosulfate. But all the others, we are going to use them, the concentrations that we calculated, to get the A, B, and C. Did I answer the question? Or not?
So for this example, you got 4.16 e to the negative 7 because you did 1/2 times the molarity of S2O3, right?
Right.
But
I did.
I'm
Yeah.
saying if you replaced the numerator of that, like
You
if I
cannot.
remember.
You cannot. Oh, if you will have a different number. You will calculate, because as soon as you say, am I doing this experiment online, you're going to get a different data. But you always need to calculate the initial rate with this formula. So let's go back to the previous here. So you will have to, the first table that you will have to complete is basically this one. And this one here is what we are using now. And you probably, let me see if you're going to have, how do we calculate this? Maybe you will have the same, depends on your data. Did I answer right? Did I answer your question, or I'm not answering it? I'm still confused about the whole lab, but it's okay. No, okay, yes, it is confusing first, but I want you to go step by step with me. Let's back up, because I want to see where is start the confusion. Basically, we are using the method that we have to divide one over the other in order to get all those A, B, and C. But because this lab has so much data, I think the best way of doing it is to go step by step, doing the report is asking you, because basically they are guiding you towards the end. So let's see, the first thing, okay, they give you this. Second, they ask you to calculate the initial concentrations. And let's do, this is clear. We saw it's just a dilution, and that's something. And then you have all those initial concentrations down. Then you know that the initial concentration of the thiosulfate is going to be used only for calculating the initial rate, only. And the rest is going to be used to calculate A, B, and C. But you have to complete this. And that's a dilution. And then what do? Basically, is when the time comes into play. So you calculate, they will ask you average time, and they will ask you for the initial rate. We saw how we calculate the initial rate with that formula. In case you forget, you will go over the last pages of the experiment. Let me share again. Because I don't want anybody to live without understanding. That would not be good. Okay. So let me, here are the calculations. So the first table, maybe we can look at the other. They'll guide you. They say, okay, this is what we just did. Then they continue explaining here. Somebody says, I guess so. I missed the last. Do we round to 2 decimal places in the average time? You basically have to do with depending on how many sig figs they give you. So let's see. In here, yeah, I would give you are right, because they actually, I would do, here it says, report average times to 1 decimal place. Report rates to 3 sig figs. So basically they are telling you that. So the average times, 1 decimal place. And the rates, 3 decimal place, 3 significant figures. Okay, so that we got it down. And then, okay. And then you're welcome. And then let's look at here. Table C, maybe we can look first at here, at this table that is clear. So we use the initial concentration of thiosulfate to calculate the rate. And then is when we use the concentration of the iodine, or what I explained at the beginning, when the last part, in order to calculate A, B, and C. And let's look at this table. This comes also in the report, but this is what is given. So this is table B. Everybody knows how to calculate the initial concentrations, because I don't want to go to table C, D, blah, blah, blah. This one is what we saw, like a dilution. Is that clear, or? Because that should be simple. Okay, good. Okay, so this is table B is easy. Let's go to the next one. Maybe in this experiment we can, okay, it's crooked and I don't know how to put it. Maybe you can look at yours if you print it here. Here they say calculate initial concentrations and rates. So the initial concentrations, we already have them. So you will have to be very, very careful. This is already, but it's not good. This, sorry, that is upside down. I wonder if I can rotate. No. The average time. So this is the data done in a different way, but because it's crooked, it's not going to help. But all we have to do is the same. This table is the one that I show you before in the report. All you have to do is the average time and the initial rate using the formula that is given here, this formula. And now will come the time that we will have to divide one over the other. I will share. Somebody has a specific question, or should I continue? Okay, so we saw this one. This one, everybody got it. Now, we saw this one, and I assume that everybody got it. So here I put 2 decimal places, but no. It says report average times to 1 decimal place. And the rates to 3 sig figs. So this is correct, 3 sig figs. Okay, so good point. This one, everybody can do it because we are going to calculate the initial rate using the concentration of thiosulfate. Again, we use this, the rate equals, it's going to continue. It's just that I want to make sure you can do these 2 tables. Okay, do you think you can complete this table? Everybody understood how to use this formula to calculate this table?
I might need extra help once you're done with helping everyone else.
Of course, when we finish this, I'll stop the recording and I'll stay because I understand this is a lot of calculations. So I'll be happy to stay. So once you do this table, it says this comes the last part, compute reaction orders. And how do we do this? Basically, this is the easiest part. You divide A2 by A1, and you have the same way we did the problem, and you calculate the ratio, and basically the same way we did that, then you calculate the rate ratio, the concentration ratio, and then the natural log and the exponent. Does it make sense, this part? This is what we've been doing like in the practice problem, how we did it. And they are helping us because they are saying, okay, divide A3 by A2. And we have the concentrations and we have the rates in the previous tables. So this is we calculate. Basically, you are going to do 3 B's, 3 C's by following what they are recommending. And then you do the average of these. And then once you have, I obtain these coefficients, you can just write the rate. The only one that is a 2 is the protons. So then this is how you write the rate. And the last part is to calculate the rate constant. And that will be just plugging in the numbers. This is the values I got. Plugging in the numbers and obtaining, as you do in any problems. And these are the units. If you don't have any questions, let's finish here. And I will stop the recording and I will stay. And also, you can always email me because you have a week to do the experiment and ask me a question, or we can meet again and I will be happy to help you. So thank you, everybody. And of course, I'll stay, as I said.